Okay, what you should have in front of you is a paper that says lattice energy free response question. And this is a sample free response question like you would see on the AP chemistry exam. What we're going to do is I'm going to walk through an answer to this sample question. And then on the next two pages, if you flip them, you have two questions to answer on your own. You will have time to answer those second two questions in class and also at home. Bring them back next time. The second two questions I'm considering a homework quiz. I want you to answer them using the steps that we're going to use to answer this first question. And so before we start and read the question, I just want to highlight, because I'm not sure if we've actually explicitly said this in this class, that when bonds are broken, energy is needed to break a bond. Okay, let's look on our energy diagram of a bond. We put this on the board. This is where the bond is at this point. I'm going to do it like a mark here on the y-axis. This point here is when the two atoms or more than have come together to form a bond. Out here they're separate, and over here they're too close together and they're starting to repel. But right here is where they're bonded together, and as you can see, that's where they're at their lowest energy point. So if you break this bond, you're either going to go this direction or you're going to go this direction, but either way, you're moving up the y-axis in terms of energy. So to break a bond, you need energy to separate two atoms or two ions. And when we talk about lattice energy, we're talking about ionic bonds. When a bond is formed, energy is released. So when these two things come together, they're here on the y-axis. When they come together, their combined energy is down here. So energy's gone from up here to down here. So that energy had to be released. The energy went from high to low, so some energy was released. So when bonds are formed, energy is released. We consider that exothermic. That's the same for if a covalent bond is formed or whether an ionic bond is formed. Okay, so we're going to use that in our explanation. And the fact that when bonds are formed, energy is released is why you see your lattice energy being exothermic when you did your worksheet, because lattice energy is the measurement of when gaseous ions come from being very far apart and come together to form an ionic bond in an ionic crystal structure. So bonds are being formed when a lattice is being formed, which is why those energies, if the lattice is stable, are negative. Okay. So let's read the question in front of you. Based only upon lattice energies, explain in detail why the thermite reaction involving elemental aluminum and iron 3 oxide to produce, I spelled that wrong, elemental iron and aluminum oxide is an exothermic reaction. Okay, that's the question. The hint is you must use Coulomb's law and electron configurations in your response. They're not going to tell you this on the AP exam. Okay, and I've given you a little hint here with Coulomb's law. We have the force, electrostatic force of attraction. Sometimes charge is represented as Q's. Sometimes it's represented as the letter Z for nuclear charge or Z effective nuclear charge. Either way, you know that force is directly proportional to charge, which are these two Q's. The K is a constant. Okay, if the K wasn't there, you'd have to write force is proportional to Q1 over Q2. And this radius down here, that's distance. That's the radius between, if this is the distance from here to here between these two charges, the radius is half of that. So technically, Coulomb's law is the force of attraction equals a constant times the two charges, 1, 2, divided by the radius squared. This radius squared is your distance. We've been saying force is directly proportional to Q1, Q2, the charge, and force is inversely proportional to 1 over distance, which is the same as 1 over r squared. So this is your hint. And now don't be confused by the question here. It sounds complicated, but break it down. Why the thermite reaction? That's just the name of a reaction. You don't need to memorize that or even concern yourself with it. It tells you the reactants and the products. I'm going to jot those down here. Elemental aluminum, Al, element from the periodic table, aluminum, the name, and iron 3 oxide plus, and you know how to write iron 3 oxide. It would be Fe plus 3, that's what the 3 means. Oxide is minus 2. Move the charges down. So plus Fe2O3, so you can decipher that. To produce, that's an arrow, elemental iron, that means an element from the periodic table, iron, Fe, as a solid, and aluminum oxide, Al2O3, aluminum, you would write that the same way as you wrote iron oxide, you'd figure it out the same way, is exothermic. Okay, so that's your reaction. So you read the question and we wrote an equation to help us decipher it. Now we're going to follow the steps on the page to answer this the way you would on the AP exam. So first thing you want to do is answer the question directly. Okay? So that's what we're going to do first. Then we're going to define any terms that will be used in the response to the question. And then we're going to offer proof of our answer. So it's not just us saying something, but we're going to say why, and that's where we'll use Coulomb's law and electron configurations. So, but remember, answer the question directly first. The question was, explain in detail why the thermite reaction, blah, 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 is an exothermic reaction. Okay, the answer is the thermite reaction is exothermic because, so you're writing a sentence to say you chose, it said, why is it exothermic? It's exothermic because, and then you're giving an answer. The energy input needed to break the lattice energy of iron 3 oxide is less than the energy output, the energy released, for the formation of the bonds of aluminum oxide. So this gets back to what we talked about at the beginning. The energy needed to break the bonds in iron oxide. Okay, and I've written the reaction here. The energy needed to break the bonds in this solid, these ionic bonds in this ionic lattice, is less than the energy that's released when these bonds are formed. So that answers the question. Then we're going to say why. So you may want to pause the video so you can write this down as an example. And then we'll go on. Okay, now we're going to define terms. What is lattice energy? Well, you have this hopefully on your vocabulary sheet. Lattice energy is the amount of energy needed to break apart a solid ionic compound. In a solid ionic compound, you have, I've shown you that picture of the red and white balls in the structure. That's a lattice, and the bonds between positive and negative ions must be broken. And actually this is not, now that I'm looking at it, I took this from somebody else. We're defining lattice energy as the opposite of this. We're defining lattice energy, and we defined it yesterday as the amount of energy that is released when the bonds are formed. But you can see some people define it as the amount of energy needed to break apart the solid ionic compound. So be careful in your definition to define what you mean by lattice energy. Okay, most people define it the way we do, lattice energy of formation. However, some people define it as the opposite. When you break the bonds in a lattice, the bonds between the positive and negative ions must be broken, and the ions go from the solid state to the gas state. This is important either way. The lattice energy is directly related to the product of the two ion charges. So this is Coulomb's law, and inversely related to the distance between the nuclei of the two ions. So in this answer, they defined lattice energy. You could, if you defined it like this would be fine, or you could define it the way we did, as energy being released. When it's released, it's exothermic. When it's needed to break apart, it would be endothermic. But either way, it's this part here that's very important. It's related to Coulomb's law, and you're saying in your answer how it's related. Okay, finally, the third part. You need to say, give proof of why your answer is correct. And this answer, which we're going to read out loud, is similar to question 7 on the answer quiz, the entrance quiz, the bonus quiz that you took the other day, and questions 11 and 12 on the worksheet that you had to do for homework, and that I talked about in a video that I posted late Wednesday night. So let's read it. The product of the charges of both iron 3 oxide, that was the, here, iron 3 oxide, so iron is +3 and oxygen is -2, and aluminum oxide are both the same. You have aluminum oxide, this is +3 and -2. They're both -6. So the charge is not going to create a difference in your force of electrostatic attraction. The charges are the same for both of these. The difference in lattice energy between the two substances is the result of the distance between the nuclei of the ions. The radius of the -2 oxygen ion never changes. It's the same in both, because the oxygen ion is the same size no matter where it is. However, the radius of the Al+3 ion is smaller than the radius of the iron ion. How do we know that? This is where you're using electron configurations. Because the electron configuration for, oh, help if I had the whole thing written out. The electron configuration for, this is for the aluminum ion, Al+3, is 1s2, 2s2, 2p6. That's the ion, because the ion has the same configuration as the noble gas that comes before it. So therefore, the aluminum ion contains fewer energy levels and fewer shells than the electron configuration of the iron ion, which is, I summarized it by using the noble gas configuration, argon plus 3d5. So, because the aluminum ion has fewer shells, it's smaller, and therefore the force of attraction, which is inversely related to distance between the ions, the force of attraction in the aluminum oxide, let me make sure I'm not confusing you, let's pause. So the aluminum oxide, which has this is a typo, smaller distance between the two nuclei, has the greater lattice energy. And it was aluminum oxide that was formed in this reaction. So the energy that is released when you form this is greater than the energy needed to break this, because this has the greater absolute value lattice energy. Okay, so now you are going to use these steps, answer the question, define terms, and offer proof of your answer for the homework quiz. There's 2 questions on the homework quiz. You can leave this up and copy this if this is helpful, but what I want you to do is think about Coulomb's law when you're answering questions about lattice energy and any other evidence that you need to use. So for the first question, you have to calculate lattice energy, and it says to include a Born-Haber diagram, which is the diagram with the arrows. I don't need you, if you don't want to include a Born-Haber diagram with the arrows going up and down, you can use Hess's law and just write out each equation and show how the things cancel so that you end up with the final equation, which is the ions forming the ionic solid, and add up correctly the lattice energies to get the right answer. So you don't have to write the diagram, you can just show Hess's law, how everything cancels. All right, have fun. See you on Monday. Goodbye.